Okay, good afternoon, everyone. We're going to go over all of Chapter 9, which is nonlinear systems. And I'm not going to obviously go through all the details, but we'll give the kind of the highlights, and you can work through the details on your own. First of all, what do we mean by nonlinear? Nonlinear systems is kind of like saying we are now studying non-elephant biology, right? I mean, an elephant is just one very, very specific type of life, or maybe non-elephant zoology. So an elephant is one particular animal, and you can spend a lot of time studying elephants, but the great majority of zoology is things that are non-elephants. And similarly, we've studied linear systems, not only linear systems, but linear systems where we have constant coefficients in front of the x and the y. Very, very specific, okay? It's interesting that we can still do as much with it as we can. But now we're going to get into the rest of the world, the rest of nature, the rest of reality, and see that most things involve nonlinear systems. And kind of like we did with the pendulum, we're going to show how you can take these nonlinear systems and then approximate them with linear systems, which is back into our familiar ground again. So let's get going. So let's go back to our population problems. We're going to begin with rabbits and sheep. We'll let x of t be the number of rabbits and y of t be the number of sheep at time t. Okay, so we'll assume that they're on this land, and let's just kind of think about how this goes again. So x prime, if there were total amount of grass and space, and I just saw something about a story about America on Benjamin Franklin, and he said given all the space that there was in America back in the 1700s, he was expecting it to be exponential growth, grow I forgot how much it was, 10% a year or something like that, and within a couple generations overpopulate England and such, which was the big country at that point. So the point is, if you have lots of space, lots of food, lots of resources, there's going to be exponential growth. But in general, you don't have that. And so instead of having this exponential growth, I'll just write it like proportional to x. This is your exponential growth, where the rate of growth is proportional to what's there. And that's what we started off with at the beginning of the course. But then we said, yeah, but in general, you're going to have some carrying capacity, and so with that carrying capacity, you end up needing something like this. And so basically, what you're saying is that when the population is small compared to the carrying capacity beta, then this is going to basically just be like another constant there, and it's going to be roughly exponential growth. So it's going to grow like this. But as you get closer and closer to beta, then this gets closer and closer to zero, so the rate of growth decreases. And so it goes like that. So you get that logistic curve, which we discovered back in an earlier chapter. Okay? So that's what happens if you just have rabbits. But now, what happens if you have sheep? You still have the same carrying capacity, but now the carrying capacity is being filled not only by the rabbits, but also by the sheep. So you're going to have something like this, where both the sheep and the rabbits are influencing the carrying capacity, and so that's roughly the sort of equation that you get, where you can have, again, constants in there, various ones. These can all have various constants, and the same sort of thing holds for the sheep. What's the rate at which the sheep grow? Okay, so we're going to have let's call all these ones there, and then we'll call this alpha 2 y. There's your exponential growth you'd have if there was nothing, all sorts of resources, and then you're going to have some sort of a carrying capacity due to the fact that you've only got limited food and grass and so on. And then as soon as you include the rabbits, then they're going to influence that carrying capacity as well. So that's the idea. So let's put in some numbers just to make it specific. And the numbers that I chose were x times 3 minus x minus 2y. So I chose very small numbers just because I wanted things easy to work with. And this is going to be y times 2 minus, what do I have there? Y minus x. Okay? And I gave some kind of justification for those numbers in the book, and you can consider them as thousands or millions or something. If you want to think of these as being more than just 2 rabbits, you can think of it as 2,000 rabbits and 3,000 rabbits and 2,000 sheep and so on. Okay, so that could be in thousands or in millions. So there's roughly the idea. Okay, so there's what we're going to have, and so then the question is, how do we go about solving that? So the first thing let's go ahead and multiply this out. If we do, we're going to get what? 3x minus x squared minus 2xy. And then here we're going to get what? 2y minus y squared minus xy. Agreed? So those are the equations. And now, as always, we're interested in fixed points. In the past, we've always had fixed points just at the origin. Okay, our origin has been our fixed point, and everything else kind of revolves around that. Now we're going to allow for the fact that that you could have fixed points at other places in the plane as well. Maybe, for example, when you have 20 sheep and 50 rabbits, maybe that's where the population stays, and so on. So there might be other fixed points. So the first thing we need to do then is to find the fixed points. So the way you do it is you have to kind of be methodical and say, what are all the different places and ways in which this system of equations can both be 0? If this is 0, then x prime is 0, which means x doesn't change. And if this is 0, that means that y prime is 0, which means that y doesn't change. So that's the fixed point. If this is 0 and this is 0, that means these derivatives are 0, and the derivative is 0, that means the function doesn't change. So let's find them. An obvious one is going to be 0, 0. See that? When x is 0 and y is 0, that's going to be 1. What's another one? Another one, we can let x be 0. Okay, so that makes this one 0. So now, what are the other choices for y? Well, let's see. If x is 0, we already had y is 0. So if x is 0, then another choice for y would be equal to 2. See that? If x is 0, then this one is going to be 0. And then if y is equal to 2, then that one will be 0. So that one works. Okay? Another one, we can let y be 0. So that takes care of this one. And now if y is 0, then what does x have to be? Well, we've already had x equals 0 there. Another option for x would be x equal 3. So there's one. And then the final one would be if both of these things are 0. So basically we're looking at kind of all 4 cases. This and this, this and this, this and this, this and this. So this is the one that's left. And so what do we have? We have x minus 2y would be equal to 3, and x plus y would be equal to 2. Agreed? That would make this 0 and also make that 0. And then if you, let's see, if you, did I do that right? X plus y, let's see, bring these over, x plus y is equal to 2. Oh no, it's x plus 2y is equal to 3. So now you subtract this equation from this one, and you're going to get y is equal to 1. If y is equal to 1, then we see that x is also equal to 1. So there's your 4th fixed point. Okay, so those are 4 different places on the plane where if the population started at this population right here, it would stay there forever. If it started at 1, 1, one rabbit, say 1,000 rabbits and 1,000 sheep, it would just stay fixed there. It would stay there forever. Similarly for all these. The question is, what happens for the other values in the plane? What happens with them? So what we need to do then is to say, okay, these are each fixed points. We need to kind of analyze these and go through what we did in the last chapter around each one of these points. We find a linear system that's centered around each of these points. And I'm not going to go through all the theory, that's in the book, but I'm just going to go through the method. Here's the method. Let this be equal to the function f of xy, and let this be the function g of xy. I'll give you the results here. Okay, here's what you do. What you want to do is, you want to take the derivative of this function with respect to x and with respect to y. So to take it with respect to x, here's the notation. You put a little x down there to indicate that you're taking the derivative with respect to x, and then you think of x as being your variable and y as being a constant. So if x is a variable and then y is a constant, and you take the derivative, you're going to get 3 minus 2x. And then here, x is the variable, y is a constant, so it's going to be minus 2y. Okay? This is called the partial derivative, by the way. It's called the partial derivative because you have a function of two variables and you're taking the derivative with respect to just one variable. So that's called the partial derivative with respect to x. Now we want the partial of f with respect to y. So we think of y as being the variable and x as being a constant. So if x is a constant, then the derivative of this is 0, the derivative of that's 0, and you're just going to get negative 2x. Negative 2x. Okay? Let's do the same thing with y. What's the partial of f with of g with respect to do the same thing with respect to g. What's the partial of g with respect to x? X is your variable, y is a constant, so the derivative of that and that are both going to be 0. X is the variable, and so it's just going to be a negative y. Okay, and then finally, the partial of g with respect to y is going to be 2 minus 2y. And then the partial of this respect to y is going to be minus x. Okay? So it turns out, and this is what, I won't go through all the theory here, it's in the book, but basically it turns out that it's called the Jacobian. The Jacobian, I'll just write it as J, and let me use the same notation I have in the book, if I got it here handy. Do I have it? Well, I'll just write it. The Jacobian is this matrix. It's a matrix that you get by putting these two partials in the top and those two in the bottom. So these two in the top and those two in the bottom. So when I think I have room enough to do it here. So it's going to be 3 minus 2x minus 2y. And then here it's going to be a negative 2x. And then here it's going to be negative y. And then here it's going to be 2 minus 2y minus x. So there's your Jacobian. And basically, here's the cool thing. What we've done is we've really linearized it. We've really it's kind of what we've kind of done is we've said, okay, if you have some sort of a function and you want to know where that how close that function is here to the value at this point. Do you remember doing this with differentials in calculus? If you know the derivative at this point, and if you know the value of the function at this point, and you want to find the value of the function at that point, then you can get pretty close to it by just taking the value here and then taking the slope at this point. And if you take the slope and just ride that tangent line up here, this value right there is going to give you something pretty close to the value of the function. Because if you're close by, then that tangent line is going to be awfully close to the graph. And that's effectively what we're doing here. We're taking this is a surface in two dimensions rather than one. Rather than a one-dimensional line, it's a two-dimensional surface, but we're basically doing the same thing. We're saying if we know the value at a point, then what's going to be the value close by, and you just take the derivative and go off in those two directions, okay? So to learn this, to get a better appreciation of this, you need Calc 3, but this is kind of the upshot of it, okay? So the derivatives allow you to kind of go off and give an approximation for the value of the function here, given that you have the value of the function there. So that's what we're going to do. We basically want to imagine what this graph is like. We're kind of going off and saying, okay, it's pretty close to looking like that in the x direction. And then in the y direction, maybe the graph looks like that. Maybe the graph looks like this. And so the tangent line is going to be very close to it. In the y direction, it's going to be close to that tangent line. So that's what you're doing when you're taking the derivative there. So in particular, let's look at one particular case here. What's the one I did in the book? I think I took the point 0,2. So let's take this particular fixed point and let's evaluate it. And so the point 0,2, and so the Jacobian evaluated at the point 0,2 is going to be, stick in a 0 for x and a 2 for y, and you're going to get 3 minus 4 is going to be a negative 1. It's awfully easy to make mistakes here. Let me just watch it, okay? Stick in a 0 here, and you're going to get a 0. Stick in a 2 here, and you're going to get a negative 2. And then when you stick in a 0 for x and a 2 for y here, you're going to get a negative 2 again. Is that right? Negative 2. Okay? So there you go. So basically this is the behavior of this system close to this point. We've basically found the behavior of this system close to the point 0,2. Okay? So at the point 0,2, we can evaluate this just like we did in the past. We can do what? We can say, oh, okay, tau is equal to what? Negative 3, which is less than 0. And what else? Delta is equal to 2, which is greater than 0. What's the last thing we need? I think it's tau squared minus 4 delta is going to be what? 9 minus 8 is equal to 1, which is positive. Let me make sure I've got all the same numbers. And so you look back in chapter 8 on to our figure there, and you see that that's going to be an attracting node. Okay, the fact that remember that our diagram there, we had something like this, and so this was delta right here, and this was tau. And so we've got delta is positive, so you're over here. And then you've got tau is negative, so you're down here. And tau squared minus 4 delta is positive, which means you're down there someplace. And that is the, let me just check, that is the attracting node. Yep, attracting node. Okay, so here's the point. You're going to do this for you're going to first read through it, the textbook, and read through this whole example, and then you're going to do your own. But at the point 0,2, here's your x-axis. here's your y-axis at the point 0, 2 right there, you've got yourself an attracting node. And you can find the eigenvalues and eigenvectors, and you can kind of get a sense of, just like you did in the previous chapter, kind of get a sense of which way are these trajectories coming in towards the point 0, 2. Okay? And so you'll do that for each of these 4 fixed points. Okay? Here's 0, 0. Here's 3, 0. And then here is 1, 1. Okay? And let's see, I won't spill, well, maybe I will spill the beans here. Here's what, once you read it, this is what you're going to find. Let me just make sure that we're still connected. Yeah. You're going to find that this is another attracting one here. This is an attracting node. This is a repelling node here. It goes off like this. And this one right here is a saddle point. So it turns out that, and those two eigenvectors look kind of like that. So you kind of put all this behavior together, and then you just kind of see what the trajectories do. This is called the phase portrait. And then you can kind of see, it's going to come in along here, you're going to go out along this one, and so it's going to go like this, and these are going to go like this, and kind of go like that. And so after you've done all the work, you see that basically what it shows is, and this is all the work that's done in the book, is that basically if you have sheep and rabbits living together, one of two things is going to, well, actually several things are going to happen. Much, much more likely than anything else, the population is going to go to either, say, 3,000 rabbits and no sheep, or no rabbits and 2,000 sheep. So, and this is noticed in nature. In nature, you find that quite often when you have two different animals, species that are both competing for the same resource, that one of them will die out. One will outcompete the other one, and the one will die out. Not always. It kind of depends on other things, but that's often the case. Things go, so if you started off with 0 of each, of course, then it's just going to stay 0. You're not going to get any population. If you just happen to be right there at that fixed point, and you don't move from that at all, then you can stay with, say, 1,000 of each. And if you happen to start right there, you'll stay at 3,000 rabbits. And if you start right here, you'll be at no rabbits and 2,000 sheep. But for everything else, I guess there's a real interesting, there is a line, there is some sort of a curve, I should say, that might come right in towards that. But it'd be very, very hard to find exactly what that curve is. If you're even a little bit off of that curve, you're going to end up either going this way or this way. That's kind of like a knife edge. It's like trying to balance a knife on its edge. It's possible it's possible in theory, but in practice it'd be very, very hard to do. Okay, so the same thing here. You have a knife edge coming up there. Okay. So anyway, so that's what you're going to do, and you're going to do a problem. The book goes through this whole problem in detail, and then you'll do the same thing where you change these numbers to, I think it's 8 and 5, and you'll do the similar thing. Okay, so that's section 9.3. So then 9.4, now you have rabbits and foxes. Okay, so another type of situation. Now you don't have a situation where they're competing for resources. Instead, you have one where one is competing to stay alive, right? So let's think about it like this. Let's think, okay, if you didn't have any foxes at all, then again these rabbits are going to just multiply prodigiously and just kind of grow exponentially. Okay, so that's going to be your exponential growth, where the amount of increase depends on how much is there. And again, that if you remember doing this, you're gonna let me just remind you, dx dt is equal to alpha x. You separate variables, integrate, you get the ln of x is equal to alpha t, x is equal to e to the alpha t. See that? So whenever you have a situation like this, you get yourself exponential growth. Okay, I need to get myself another marker here. Okay. So anyway, with foxes, unfortunately, those rabbits aren't going to be able to necessarily keep growing like that because the foxes are going to eat them. But of course, the foxes are only going to eat them if they happen to see them, happen to meet them. And so basically, meeting them is going to happen kind of in proportion to how many of each there are. If you just think of these things as being kind of random animals that are bumping around, well, the more of these you have, the more likely they are to meet. The more foxes you have, the more likely they are to meet. So as you multiply the two together, the larger this product is, the more likely they are to meet. And assuming that when they meet, the fox is going to say, "Hey, how are you? Now I'm going to eat you." It's going to look something like this, where the rate at which the foxes eat the rabbits is proportional to the amount that they meet. So that would be, there's your differential equation that takes care of the rabbits. And so we're just going to assume here that there's no carrying capacity that's even needed because the foxes are going to eat the rabbits before they even get up to a carrying capacity. Okay, so that's part of this model, is that the foxes are going to keep their population down. What about the foxes? Again, let's put like that. If there were no rabbits at all, then the foxes would die out. Okay, let me put it over here. Okay, I'll assume all the constants are positive here. So if I want one to be negative, I'm going to put a negative in front. Let me call that alpha. Okay, so if there are no rabbits, the foxes would die out, and they would die out kind of proportional to how many foxes there are. Okay, they're just going to die out just in the same way in which radioactivity dies out. The hardiest ones are going to continue living for a little bit, but eventually they're all basically going to be dead. So that's what would happen. But again, luckily for the fox, they happen to meet the rabbits. And when they meet the rabbits, they eat the rabbits. And once they eat the rabbits, they're more likely to live. So that's going to be the differential equation that models the foxes. And so similar to what we did before, you can put in values. 6, 2 is what I have. Again, I chose easy ones. And 2, 10 I put in. I put in a 2 right here. Oh, this is the same. And then minus 10. 10y, right? Is what I've got. Okay? So, similar sort of thing. You find the fixed points. And once you find the fixed points, then you analyze each of those fixed points. In this case, I think there's just 2 of them. And you analyze those. And by the way, right here, just to make it easier to do the fixed points, go ahead and factor a 2x out of that. You're going to be left with what? 3 minus y. And factor 2y out of here. And you're left with what? X minus 5. Again, it's so easy to make mistakes. Make sure. 2x, 3 minus y. 2y, x minus 5. Yeah, okay, so that makes it pretty easy to find the fixed points there. I'll let you finish that off, and that's all in the book. And then you can analyze that as well, okay? Going through the same procedure we did in the previous one. In fact, let's go ahead and just play with this just a little bit more. So here, this is your f of xy. This is your g of xy. And so what are your fixed points? If this is 0, then this can't be 0. So the only way for this one to be 0 is when y is 0. If this is 0, if y is 0, then then this can't be 0, so x has to be 0, so you have the same thing there. So the only other one then is if both of these things are 0. So that would be what? X is equal to 5 and y is equal to 3. Okay, so those are your two fixed points. And so so let's just oh, this is so much fun. Let's just play with it. So the partial of f with respect to x is going to be, this is the easier place to do it, partial with respect to x is going to be 6 minus 2y. And the partial with respect to y is going to be negative 2x. Agreed? The partial of g with respect to x is going to be what? 2y. And the partial of g with respect to y is going to be what? 2x minus 10. Okay? So your Jacobian in general is 6 minus 2y, negative 2x, 2y, 2x minus 10. We'll get another marker again here. Okay, might be I need to go get a brand new one here. Okay, so let's do this one. Let's evaluate it at 5, 3. So the Jacobian at 5, 3 is going to be what? Oh, I don't know. No, I'm gonna. The teacher in me wants to do it for you, but this is all the fun part. So you go ahead and evaluate the Jacobian at 5, 3, and then find out what the type of fixed point is, and also at 0, 0, find out what the fixed point is, and then go from there. Okay, so that's the fox hare problem. By the way, the problem that I have for you in the book, I mentioned this. Okay, a friend of mine noticed this, so I need to give credit to him. I won't mention his name since I don't know if he would want me to or not. dy dx is equal to dy dt over dx dt. That's the beautiful thing about okay, it froze on me here, and I caught it. So let me just finish what I was saying here. The dy dx. This is a separable dE. Notice, because you can write dy dt over dx dt. Here's your dy dt right here. Here's your dx dt right there. Notice it's separable. You can first cancel off the 2's, and then you can bring all the y's over here with the dy. It's going to be what? 3 minus y over y. And then you bring the dx over here with the x's, and you're going to get x minus 5 over x dx. And then you can integrate both sides. Okay? So integrate both sides, and when you do that, you're going to get yourself, again, I won't finish it for you, but you're going to get yourself an equation. And then you can go to Decimus, and you can use Decimus to graph it for you, and you should get the same graph that we got in the book, doing it our former way. Okay, so it's kind of cool. And the one thing you should notice is that when you find the antiderivative of both sides, there's going to be a constant for each one. So you don't need a constant on each side, but you can have a constant on just one side, and then check to see what the graph looks like for various constants. So when you use Decimus, let the constant be 0 and get that graph, and then let the constant be 1, 2, 3, 4, 5, so on, -1, whatever, and see once what happens to your various graphs. Okay, so something kind of fun to see. Okay, so that is the kind of an overview of 9.4. Then in 9.5, we then ask the question, will these linear approximations always work? is it always valid to use a linear approximation? That's always an important thing to ask in mathematics. You do these I shouldn't call them tricks, methods. You do these methods to solve problems, but especially when the method involves some approximation, then the question is it valid or not? Okay? And so let's look at this diagram that we had again back in chapter 8, I guess it was. And we had this thing, and this was delta here. Delta. This is tau. This is tau squared minus 4 delta equals 0. Is that parabola? And recall that we had various things. Everything on here was a center in particular. If tau was equal to 0, you had a center, and then you had multiple fixed points if delta is equal to 0, and so on. Okay? So here's the point. Here's the point. If your linearized system, you start off with some sort of system and then you linearize it. If your linearized system is safely in it's called topological term is the interior. So you've got space around it, basically, okay? You've got neighbors around it. You're comfortably in the middle here. If you're somewhere in the interior of this region right here, then even when you linearize it, the linearization and the actual thing are going to be in that same region, okay? Because the two are kind of arbitrarily close to each other, and so whatever one is, the other one's going to be the same. So even though the numbers might be a little bit off, it's still going to have the same behavior. Whatever the behavior is up at that point, let me just check it as long as that's a repelling spiral, okay? So if you happen to choose something up here, it's going to be a repelling spiral, so you're safe. But if when you linearize it, if you happen to end up right here, right there on that line, then it could be that what you did was your real one was maybe over here. I'll just take this, and when you linearized it, it ended up right there. And so even though they're very close together, they're going to have two different kinds of behavior. The behavior of this is going to be a center, and the behavior of this is going to be an attracting spiral. So the point is, if you end up right on one of those lines, then it could be the case that you end up with your linear approximation might have a different behavior than the actual thing. And just to show you that this actually can happen, I've got an example there for you. It's here's what it is. Get rid of the rabbits now. We have x prime, or x dot, is equal to, and that's our f of xy, we'll call that for convenience, is going to be negative x cubed minus y. Okay, and y prime is equal to, that's your g of xy, which in this case is just equal to x. Okay? So if you go ahead and find the Jacobian and evaluate the Jacobian at the point 0, 0, this is already in the book, so I'm giving you what's already there, but you're going to find that you're going to get this. Okay? And if you get that, then you notice that tau is equal to 0, and delta is equal to 1, and you're going to end up with a center. Okay, so your linearized system, when you go through the work, and so this is part of your problem in chapter 9.5, is to go through and take the partial derivatives, put in 0, 0, and see that you get that, and you're going to get a center. So that's what the linearized system predicts, okay? But you can show, and that's what the rest of the problem is, that this thing actually does not give you a center. And the way you do it is, you first write it in terms of polar coordinates. And this is one thing that we haven't talked about in the course. So let me just give you a brief introduction to polar coordinates. If you have a point on the plane like that, the way that you typically express it in calculus is you call it xy, where x is the distance from the y-axis, from the origin, and then of course y is the distance up, and that pair gives you the address of that point. Another way to get the address of that point is by taking this angle here, the angle, the positive angle. Positive, of course, means counterclockwise. Starting at the positive x-axis, so starting right there, take that angle, and then you let this be your radius, a positive number right there. So if you know what this angle is and you know what this radius is, then that's also another way to express the value of that point. And that's called polar coordinates. And there's some really nice graphs that it's much easier to write them in terms of polar coordinates than it is rectangular coordinates. For example, a circle of radius 5 would be like this in rectangular coordinates, but it's just this in polar coordinates. How easy is that? R is 5 and theta is unrestricted, so you go all the way around and you got your circle of radius 5. So there are some things that are much nicer to express one way than the other, okay? But the point is, what are the relationships between these? Okay, just seeing the trigonometry here. What's the relationship here? X over r is equal to, let's see, what is that? Adjacent over hypotenuse is the cosine of the angle, and so that means that x is equal to r cosine theta. Okay, actually unit circle. That's even more clear. Similarly, y is equal to r sine theta. Okay, so those are the relationships between x, y, and r theta. So the first thing you're going to do is you're going to write this expression in terms of polar coordinates. Okay, and so putting in this and this for x and y is no problem. How do you take the derivative of this? You've got x cosine theta, that's what your, r cosine theta, that's what your x is, and we want to take its derivative. So how do you take its derivative? Recall that you have to use the product rule. The product rule says what? You take the derivative of the first times the second plus the first times the derivative of the second. The derivative of the cosine is the negative sine. And then we have to use the chain rule. Negative sine theta times the derivative of theta, which is d theta dt. We could either write it as d theta dt or theta prime. Okay? So that right there would go in for x prime. That's equal to x prime. Okay? So that's on one side, and then you put this on the other, and you get an equation, and you can do the same thing for y. Once you have that, here's what you're going to have. You're going to have a bunch of stuff times r prime here, plus a bunch of stuff times theta prime is equal to a bunch of stuff. Let me just put a, b, and c in there just for kicks, just for giggles. It's going to be a bunch of junk in there. Same thing here. You're going to get d r prime plus e theta prime is equal to f. Okay? And Kramer's rule tells you how you can find the values of these things using Kramer's rule. Here's what Kramer's rule says. Kramer's rule says if you want to find the value of r prime, you take one determinant over another determinant. Okay? The determinant on the bottom is just what you get by putting in a, b, d, and e. Those things right there. The determinant on the top, since you're trying to find r prime, you replace a and d with these two things. So it's going to be c and f right there, and these stay the same, b and e. And so you evaluate this determinant, you evaluate this one, and then you simplify, and you're going to get your r prime. You can do the same thing for theta prime, where the bottom is going to stay the same, but now you're going to replace b and e with those two things. They're going to go right in here. So let me just do it for you. So theta prime is going to, bottom is the same, and now you're going to put c and f in, these things are going to be a and d, and these are going to be replaced with c and f. Okay, so that gives you that. So those are two different things I mentioned in the book, and so there's Cramer's rule and also polar coordinates. So that should be what you need in order to finish the problems in this section, and there you go. Very good.